Good day students, I am Somasundaram from Bharathidhasanar Matric Higher Secondary School, Arakkonam. We were discussing about the second unit, quantum mechanical model of atom. What about the spectrum? It is a wide range of spectrum, wide range. So, up from cosmic rays to radio waves. These are all called electromagnetic radiation, electromagnetic spectrum. What are they? The first one, the highest energy is for cosmic rays. The next one is X-ray, gamma ray. Next one X-ray, then UV, and then the very useful region that is called as visible region. Without this visible region, we can't see things in our earth. What is the main source of visible region? Yeah, it is our sun. Okay, without sun, we can able to see the objects in our earth. Next, IR, infrared, then microwave, then the radio frequencies are there. Okay, so what are the uses of this electromagnetic radiation? Gamma rays, is there any use? No. We are using to identify the distant planets, the structure of distant planets, what are the elements present in the distant planets. We are using alpha ray for that. Next one, X-ray, yeah, identifying the structure of our bone. If any fracture happened in our bone, we can use X-ray. Next one, UV, ultraviolet. So ultraviolet, it is also coming out from sun. Our ozone layer is preventing UV ray entering our earth. Anyway, because it causes cancer to our skin. Next, visible region. Visible region is very useful. Without visible region, I said, we can't see any object. Next, IR, infrared. So it is used in our TV remote controls. So TV remote control generating the IR ray, which is have been observed by the TV, and it is the programs may be changed. Next, microwave. They are used to increase the temperature of the particular object. So microwave oven. Next, radio waves are used to transmit the messages, radio as well as our dish connections. Wavelength lambda. When an electromagnetic radiation propagating through the space, you can clearly see the waves. So the distance between the two crust, adjacent crust, is called as wavelength lambda. The wavelength may be expressed in meter, that is the unit, meter or else nanometer or Armstrong. So I will give you the conversion, how to convert meter into nanometer or nanometer into meter. We all know 1 meter, that is equal to 100 centimeter. Next, 10 power minus 9 meter is called as 1 nanometer. Next one, 10 power minus 10 meter, that is equal to 1 Armstrong unit. Okay, these are all the different units have been used for wavelength. Frequency. What is frequency? See, we have fixed a straight line here. In 1 second, how many waves are crossing this space? It is called as frequency. For higher wavelength, frequency is lesser. For shorter wavelength, frequency is higher. That is nu, frequency. What is the unit? Second inverse. Or else hertz can be used. Now we can relate wavelength with frequency. What is that? Nu is equal to C by lambda. This is the relationship between wavelength and frequency, C by lambda. So we can introduce this C by lambda value into the Max Planck's equation, that is E is equal to h nu. So it will become E is equal to h C by lambda. So what about the energy and wavelength relationship? If the wavelength is more, energy will be decreasing. If the energy is more, wavelength will be lower. So this is atomic spectroscopy. I have given some example here. When you use noble gases inside the Coolidge tube, inside the discharge tube, you will get different colors. It is because of atomic spectra. So what is happening in atomic spectroscopy? So in an atom, there are so many electrons available. They may present in a stationary orbit, stationary level. When an electron is irradiated with energy, light energy, what happens? It may go to the higher energy state. When it reaches the higher energy state, it won't be staying there in so much time. Okay, it has to be returning to the stationary state. When it is returning from higher energy state to ground state, it emits energy in the form of light. So this is the observed light what we are seeing when we introduce an atom into a flame. Okay. So using these three different works, what are they? Max Planck's work, next photoelectric effect, then the atomic spectrum. Our Bohr, Niels Bohr, was predicting the Bohr's atomic model, and he was trying to overcome the drawbacks of Rutherford's planetary model. What are the drawbacks? Dual character. See, this is not drawback, actually it is a advancement for Niels Bohr's technology. Using the three different works, Max Planck's work for energy of light as well as photoelectric effect, then the atomic spectroscopy, Niels Bohr predicted his postulates. What are they? First one, quantization about energy. In atoms, electrons are available in a particular orbit. They are having quantized energy, that is E is equal to nh nu. So for each orbit, the value must be 1h nu, 2h nu, like that only. So that is called as quantization of energy. Next one, stationary orbit. So for each electron, there is a stationary orbit. Whenever the electron is available in the stationary orbit, it won't lose its energy. Next, the quantization of angular momentum. So the allowed orbit can be identified using the equation nh divided by 2 pi. This is the allowed angular momentum. Next, as long as the electron revolves in the fixed stationary state, it won't lose energy, but we can excite an electron from the ground state to higher energy state by irradiating that electron. So thank you, students. So according to Bohr, he was able to predict the presence of orbit, but he was not correct about orbitals. So in our next class, we will discuss about the quantum mechanical model where the proposal of orbitals has been taken place. Thank you very much, students.